Well, a warm welcome, everyone. Thank you for joining here. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're going to continue our little summer series of implicit differentiation problems. If you haven't checked out the first video, it was a bit of a doozy compared to this one actually. We really cracked things open with some applied skills, and I'm pretty sure it was a calculator problem, but I didn't present it as a calculator problem, so sorry if you got a little tripped up there. With a calculator, these problems are much easier, obviously. This one is a bit shorter. We're not given the original curve. We're jumping straight into the expression for the slope dy dx. We're given this. So without further ado, let me allow you to sort of scope out the questions. Yeah, there's just two parts here, parts A and B. You can pause the video, give yourself some time to work this out. This one should be a bit shorter. It should probably only be like 7 or 8 minutes. So, and I'm being serious about it this time. Then when you're ready, you can come on back and join us to see how we did it here. Hopefully you're keeping yourself fresh with calc skills in mind. All right, let's get started here. The function f is differentiable for all real numbers. The point 3, 1/4 is on the graph of f, and the slope at each point of the graph is given by this. So like I said, we're given dy dx. This is an expression for the slope at any point. But the x and y point has to be on the graph, remember. We don't have an original curve to check with here. So presumably, and this is accurate, presumably we're not going to be expected to go back and check to find any y values or to find any x values. We are given a point, x and y, so that we do not have to rely on any other curve equation. Well, let's get into this. Find d squared y dx squared and evaluate it at 3, 1/4. So what is this d squared y dx squared? This is essentially telling us to find the second derivative, or the derivative of the derivative. And so to work with that, we're going to use this equation here, and we're going to take a derivative of both sides. Now, fortunately, dy dx is already isolated, so when we take a derivative of the left side, and then when we take a derivative of sort of the right side, that's what these are representing here, we're going to end up with d squared y dx squared. And on the right side, we're going to have a product. So we have to be a little careful here. We have y squared times 6 minus 2x. So we have y squared being multiplied by this parentheses. How do we do the product rule? You might remember from last video and from your calculus experience, obviously. The product rule goes as follows. We're going to take the derivative of the first term and multiply it by regular second term. Don't do anything to the second term. It's free. You just place it. Plus the product of the reverse of that, which means the first piece, just place it. Don't do anything with it. And the derivative of the second part. It might be even easier for you to just place those things first, which we're not going to do anything with, because you literally just take this piece, put a square peg in a square hole, and bada bing, bada boom. Same thing with the y squared here. So 1 bar indicates we're not changing it at all. 2 bars indicates we're taking a derivative. So let's take a derivative of y squared. Be very careful when you do that. It's 2y but we have to multiply by the derivative of y, which is dy dx, as per the chain rule. And then the derivative of 6 minus 2x, pretty easy, it's just negative 2. Okay, so I don't know if they want us to have it in a really particularly simplified format. I don't think so, but it is a good idea to know how to do that. So if I were to sort of multiply the 2y in to the parentheses there, I would end up with 12y minus 4xy, and that's times dy dx. Then we have minus 2y squared. This is a fairly simplified form for our second derivative. Now that's not all they want to know. They also want us to evaluate it at this point, 3 comma 1/4. So at that value, the way that we write evaluating, by the way, is we would say d squared y dx squared. Then we could put a little bar here. And you can either put the coordinate, you can put 3 comma 1/4. You can also put just sort of like the conditions that you're plugging in. So you can say x equals 3, y equals 1/4. You can do it like that. I think it's a good idea to write something like that to indicate that you're using the second derivative and you're plugging in these points. That's going to be equals to 12 times 1/4 minus 4 times 3 times 1/4. And this is all times dy dx, which I actually don't know at the moment. I will have to fill that in. We'll work on that in a second. Minus 2y squared. So minus 2 times 1/4 squared. In order to find dy dx, I have to go back to the original expression. And I can say that at the point 3 comma 1/4, dy dx is equals to, you can also write it as I just suggested, as I just recommended, dy dx, and then you can either put the point, or you can put x equals 3, y equals 1/4. Either way is fine. This is going to be y squared, so 1/4 squared, times 6 minus 2 times 3. Well, that's interesting, isn't it? Because this is going to be 1/16 times 6 minus 6, which is 1/16 times 0, or just 0. So, got some very interesting value here, because it really doesn't matter what happens in this parentheses. I'll work it out just for the sake of it. This is going to be, oh, interesting. This is going to be 3 minus 3. 4 times a fourth cancels to 1. 1 times 3 is 3. So we have 3 minus 3 times 0, as if there weren't 0 enough. So we have 0 times 0, big surprise on what that is, minus 2 over 16, or just 1/8. So we're going to end up with negative 1/8. Okay, that's part A in the bag. Now, because dy dx at this point is equal to 0, let's take a moment and just understand what that means about the curve. Since dy dx is 0 at 3 comma 1/4, let's make this a little longer. We know that the curve is horizontal there. You could also say flat. And so we have a horizontal tangent line. That's going to be kind of useful. Let's take a look at what's here. Write the equation of the normal line. You guys know what I'm going to say. I said it last episode. Whenever you read equation of the line, like equation of the tangent line or equation of the normal line in calculus, I want you to just stop, drop, and roll. Okay, maybe don't roll. You don't even have to drop. Just stop and write this expression, this equation, y minus y value equals m times x minus x value. This is the point slope equation, which is a very common form of the line that you're going to use in calculus. M stands for the slope, of course, but in this case, it's not going to stand for the tangent slope. It's going to stand for the normal slope or in other words, the negative reciprocal of the tangent slope. And that's where it's really important to understand the nature of the tangent line at the point, which is why I had you look at the derivative again. The derivative tells us that the curve is horizontal at that spot. So we don't really know what the curve looks like, but let's just say it's like, I don't know, like that. Maybe that's kind of bad. Something like that. Simple. If this is a flat point, then the normal line, which is perpendicular, must be a vertical line. And the slope of a vertical line is undefined. It approaches infinity or negative infinity, but its value is undefined. So what does that mean? That means that the normal line, in this case, the normal line is vertical. Undefined slope value. And because of that, we can use the standard equation for a vertical line, which is simply x equals blah, blah, blah. Whatever the x value is, that is going to be the equation of our line. So in this case, x equals 3 gets the job done. That is the normal line. Doesn't fit this typical format because the slope here is kind of like something over 0, which really doesn't make sense as a value. So since there's no value, because the line tangent to the curve at 3, 1/4 is horizontal, the tangent line, the normal line, which is perpendicular to the tangent line, must be vertical, and therefore its equation simply follows an x value, x equals 3. Okay, so pretty easy stuff there. I would say that that was the easier question of this little trifecta summer series that we're going to be taking a look at. No calculator was required here, just a little product rule, as is very normal of an implicit differentiation problem, plugging in some values, and then especially when we get to the second derivative, you normally have to plug in some values to the original derivative, as well as plugging in x and y values to the equation for the second derivative. So lots of plugging stuff in, just being very careful to, like I said, put a square peg in a square hole, or in a round peg in a round hole. And then here we had this use of normal line, which is slightly different to tangent line. So these are just ways to kind of get your brain practicing, rehearsing the interpretation of a word problem, as well as simple setup. Like when we have the equation of a line, we're going to use the point slope equation. Very straightforward every time. Okay, I think that's enough blab out of me. Rather brief one, so you're welcome for that. Join us next time. We're going to wrap up this implicit differentiation summer series, courtesy of a past student that I had that needed some help. And so I wrote that student some various practice exams for different units. And so we'll be taking a look at problems like that to keep you fresh over the summer. Alrighty. That'll do it for me. It's enough blab out of this man. I'll see you guys next time.